thing, and depending upon the bias being the same, you can't be exactly sure of that at all. Let's talk a little bit about what we did in order to explore some of these options. Our main motif is going to use some observed behaviors in energy simulations. And by observed, we mean real clocked behavior. So we're going to be looking at some thermostat settings that we've collected in the San Francisco East Bay, some occupancy data that we have from the American Time Use Survey, and we even have some window opening and closing data from basically teenagers that don't have to pay the bill that we tried to take a look at.
One thing I think is important to note too is the scarcity of behavioral information at any kind of fine-grained level here. Frequently we have self-reports of normal thermostat settings at one or two different points of the time or day or year or whatnot. So when we're able to incorporate data from actual observed thermostat settings, this is very unusual. It gives us an unusual opportunity to test for the potential magnitude of the effects of behavior.
The graphic that you're looking at right now is just a sample of a week of cooling set points for our houses. And the thing that I really want to point out here is that not everyone has the same thermostat settings. Not everyone is following the same pattern every day. They are bouncing around all over the place. If you can see some cyclical patterns, yes, there are some, but they're not quite as regular as is usually assumed. And the consequences we're going to show you are quite large. You're going to see a lot of variation that's due simply to having these thermostat settings change. I mean, this is going to be holding building constant, holding weather constant, and just varying around those thermostat simulations. And even more so that we're eventually going to demonstrate this little gap between your average thermostat settings and what are the kWh consequences of that, and the average of the kWh that comes out of the simulations. So let's take a look at what we saw for thermostat settings. Now, there are some assumptions that are in common use for these building energy simulations, and one of the ones that people make most frequent reference to is the residential alternative calculation method, ACEEE, which is used for Title 24. And in particular, you'll find out in one of the appendices the hourly thermostat set points. And what we want to focus on is exactly how regular these things are. I mean, if you look at those whole house set points, you see that people will set their heating set point at 65 or 68, and there's only one change during the day, effectively. When people get up in the morning, the heater goes on and then it kind of stays on until they're tucked themselves back into bed at about 11 o'clock. If you look at the cooling set points, for the most part, people are assumed to be their living conditions at 78, and then over time people leave and pump up the set point on the air conditioner, and then there's this slowly coming back down to 78 pattern that's there.
I think one thing to think about here is that in establishing these kind of standards and trying to construct models that work across a population or create expectations for the population, you're going to end up with something that looks like this. This is probably what most of us would construct. The problem, however, is if the real world is very different from these patterns, there can be the consequences that we mentioned earlier as far as policy forecasting and simulation model accuracy.
Now, we do have some observations of thermostat data. There was this little study that was done in the San Francisco East Bay, and essentially it was trying to get the equipment to work. So there are some flaws in the data collection. But what we ended up with was about 78 houses in the San Francisco East Bay. We had observations of load, total kWh used, thermostat setting, internal temperature, the mode of the thermostat, resulting in a little bit more than 500,000 observations, all between February and November 2003, with it ramping up in February and ramping down in November. But we have some pretty good coverage of thermostat settings during the summertime.
Let's put the right caveats in here too. We're not really certain about the construction of this sample. We're not claiming representativeness, but these data are so unusual that the kinds of patterns that we're going to demonstrate here, I think, are going to be ones that we're going to need to pay attention to and wonder what the distributions look like in the population and what the effects may be across the population.
So the first thing to point out is that households don't just set a thermostat, they also set a mode that's there.
So first, what are we seeing here, Jamie? Describe what actually is being represented on this graphic.
Well, one of the things that was recorded in the thermostat, besides the indoor setting, besides the indoor temperature, is what you had your thermostat doing. Having it set into cooling mode meant that if the temperature got above a certain level, AC would kick on. If it was in heating mode, if the temperature got below a certain level, the heater would kick on. And auto means if it gets out of either one of those two bands, it will turn on. But there's this other mode, off, which people often forget about. And you can see that off block right there, these blocks right here. So that an awful lot of time people actually have their thermostat in off mode. And you can see that there is some variation with the thermostat being in heating mode most frequently during February, March, and April, and then most frequently in either off or cooling mode in June, July, August, September, and then transitions over to November. You got to remember that February and November, the number of observations starts getting a little bit lower.
And to make the obvious point, off cannot be included in averages.
Off cannot, and also an obvious point that we frequently assume that if people have thermostats, that they set the thermostats at some level and leave them, don't turn them off, or that in fact if you have cooling and heating capacity and you put it on auto, and in these cases these are programmable thermostats, simply program it. It should be in the auto mode, and the auto mode is very, very rarely observed in this sample.
Now, this should give you an idea of variability of those cooling set points. Just over the course of a week, the main thing to focus on is that there is not a common set point that folks use. There's a great deal of variability. And just to focus in a little bit closer, you see that we're talking about huge ranges for where those cooling set points are. Between 70 and 85 is where you have most of those set points. It's a much wider range than is actually assumed back in the ACEEE over here.
So the other interesting thing here too, when we look at that graphic.
This one?
Yep, that one.
Uh-huh.
Another interesting thing. This is only when the thermostat is in the cooling mode.
That's correct.
So we have considerable variability across households or between households. We also have variability within households. So people are actually not sort of just always going right to the same point, or even necessarily using this as a switch, an off-on switch. We're using it as a very complicated strategy.
Okay. So let's go ahead and, oops, I like it when the buttons get slightly confused, but it's almost as good as a presentation. Now, I've gone ahead and made it so you can see the variability in thermostats in a slightly different way. So what you're looking at here is the average of the cooling set points during the day when the thermostat is in either cooling mode or auto mode. And so it's when it's not in the off position. On each day, you're going to see a little bit of variations, and what we have there is a box plot with a little dash in the middle indicating the median of the average daily cooling set points for each household. The boxes themselves cover the interquartile range that you know that between the 25th percentile and the 75th percentiles there. Those little lines extend out to give you a 90% block, and there are a couple of outliers that are there. The big focus should be that it's a huge temperature range for these average cooling set points. Everything is not the same. It's very common to see averages which vary, with 50% of the population varying over 10 degrees or something along those lines. But we also want to focus on that it's not just between household variation that we're looking at. There's also a significant amount of within household variation. And the little blue lines that may have puzzled you for a while actually connect for each individual household the average cooling set point on one day to the average cooling set point on another day. And we have a gap in our data right there. That's not there for graphical purposes. It's just that the data wasn't recorded during that time period. And you can see that households are changing from a day-to-day basis, the average cooling set point that they're actually setting throughout the day. So we're seeing a lot of between household variation and a lot of within household variation from day to day. Could be reactions to the weather. It could be that just it's somebody else in the household operating it. It could be it's just that, you know, they are using it as a switch and choosing random set points, but we are observing these kinds of things in thermostat behavior.
Yeah, sure. I mean, good point, Jamie. I think there's lots of possible explanations and probably lots of underlying patterns of behavior that are captured in this graphic. That different kinds of household dynamics that actually go into finding a set point, changing a set point, and producing energy flows that result from it.
Okay. So, main points we want to get to. People do more than just pick set point loads. We see a lot of variation between households, and we also see a lot of variation within households. They do different things on different days. They don't always do the thing, and they don't follow those ACM assumptions.